So we took that variable, ran it through Carrot class probability tree, compressed it into 5 levels, brought it back into the system, and ended up having 1 additional % increase in the area under ROC curve, which could be a very substantial increase in accuracy, something that would separate you from the winner versus the loser in the major competition. So that was kind of one side that I wanted to mention. The challenge number 2, missing values. The missing values is generally a very tough problem. And again, every major tool that we have, Carrot, Mars, TreeNet, Random Forest, everywhere there is at least some kind of measures taken into account to handle missing values. In modern days, if you have a data mining algorithm that is not capable of supporting missing values, then you're missing a major chunk of work. Because all of the real-life data sets will have all sorts of problems, and missing values is one of those big and important topics to consider. As far as I know, and I might be mistaken, but the creators of Carrot spent the vast majority of their time working out the details of missing values. And it was actually very useful because in the end, they ended up with a very intriguing approach that relies on finding so-called surrogate splits in order to back up the main splits that happen to be missing on part of the data set. It's a very tricky machinery and yet very powerful to the best of my knowledge. And I've been studying every other algorithm that we have. I know how missings are handled in Mars. I know how they're handled in TreeNet. I know how they're handled in Random Forest. Carrot has a superior way to handle all of the missing values. In fact, you can run Carrot on a data set where there are no missing values, and yet the resulting model will know how to handle the situation where everything is missing. All the other algorithms that we have, you have to have missing values as part of the learned sample in order to train the algorithm to handle missing values at the deployment stage. And if you reintroduce missingness into variables that were nice and clean at the model building step, the entire performance may collapse because the algorithm will not be able to accommodate those kinds of things. But not with Carrot, and therefore we offer a number of tricks that you can employ by running Carrot. Now, first of all, before we go into the Carrot side, the reason I have this slide is that we've learned that you cannot just discard or impute missing value information and forget about it, forget that it was there. Because oftentimes the fact that something is missing is informative in and of its own. The classical example would be the fact that the credit score is missing is usually a very negative red flag as far as modeling a credit risk and bankruptcies and defaults and fraud, et cetera, et cetera. So regardless what you do with missing values, at least go ahead and create missing value indicators, and our modern machinery, Carrot 6, et cetera, offers those capabilities. You basically put a check mark and you can run. It will add automatically missing value indicators for you. You can even run models with missing value indicators being the only predictors available to the modeling stage. And that's kind of some of these important parts here. But the missing value imputation is a more interesting topic here. And what we suggest here is that why don't you use Carrot to actually take care of the missing value imputation? Think about it. Suppose you have a variable, income. It's continuous everywhere, but the part of it is missing. In the conventional imputation, you would simply impute into the mean or the median or some kind of constant value, unless, of course, you want to drop those records entirely, but then you may run out of data before you even start modeling. But on the other hand, you can take the part of that data set where income is not missing and build a model, build a data-driven model to predict the income, and then they reapply that model to the rest of the records to essentially impute. And we'll have a data-driven, localized imputation as long as you're not overly aggressive in building those models. And CORT is one of very nice examples because it's not trying to replicate some kind of fine response surface. It simply fits these piecewise constant predictions that vary as you go from region to region. So we use CORT to basically impute all of the variables that we find interesting and important in some other ways. Of course, if you have a few missing values here and there, you're not going to see a big difference. But when you have cases of informative missingness, given the fact that in CORT the surrogates are always defined, and CORT has a superior capability to handle missing values to begin with, it becomes virtually a perfect tool to do something like that. I can tell you, if someone asked me, give me top 2 reasons why you want to have CORT in your toolbox, I would have probably said, well, reason number 1, I can get a quick and dirty picture of what's going on in my data set within seconds. And I don't have to wait hours or make some heavy configuration runs. And the reason number 2 is that I can impute everything, and I cannot trust into anything else in doing as a good job as CORT will do in this case. Well, you could do that with TreeNet, of course, but the TreeNet doesn't have the concept of surrogates. And when you have a very convoluted data set, you have to be careful with what happens when certain things are missing within the learned sample. I mean, we can discuss it. Certainly, the machinery is already there. You can do it using TreeNet. But I would still recommend CORT because I don't want to lose too much. Kind of CORT fills in general kind of rough picture without overemphasizing particular overfitting in the different regions. Well, it's a long story. We can discuss it later. Okay, now what does it lead us to? And that's a very important step of automation. We call it battery target. And it works approximately like this. You have a list of variables that you've identified as the variables of interest. Now, some of these variables may or may not have missing values. Now, regardless of what happens on the missing side, CORT will pick one variable at a time as the target and run everyone else as current predictors. And then it will rotate all variables one at a time. So if you have a set of 100 variables, in the end, you will get 100 CORT runs. Each run will explain the variable of interest based on everyone else. The only variables that you want to be careful would be high-level categoricals, because then you will run into some complications as far as collapsing runs and so on, which is why challenge number 1 supposedly fixed that part. Now, once we get the results of battery target, we get the imputation automatically because we can rely on the run that corresponds to each dedicated variable for future imputation. And that might include the deployment stage when you need to apply your models to new data sets. So you can save the resulting tree and use it to score the original data. But what is more interesting, all of a sudden you have access to studying similarity in some generalized nonlinear sense among the predictors. And let me elaborate on this a little bit more. Here is the output from churn competition and the results of running that battery.